Welcome to chemistry. Isomerism. What do molecules with the exact same molecular formula but completely different properties have in common? They are isomers. Isomerism is one of the most fundamental concepts in organic chemistry, explaining why the same atoms can arrange into substances as different as glucose and fructose, or as significant as enantiomerically pure drugs. In this presentation, we will explore the two major branches of isomerism: structural isomerism, where atoms are connected differently, and stereoisomerism, where atoms occupy different spatial arrangements. Through detailed theory, 5 interactive quiz questions, and 5 fully worked problems, you will master how to identify, classify, and understand isomers. Let us dive into the molecular world where arrangement is everything. Isomerism is the phenomenon where two or more chemical compounds have the same molecular formula but differ in the arrangement of atoms in space. The word comes from the Greek isos, meaning equal, and meros, meaning part. The two broad categories are structural isomerism, also called constitutional isomerism, where atoms are bonded together in different orders, and stereoisomerism, where atoms have the same bond connectivity but differ in their three-dimensional spatial arrangement. Structural isomerism includes chain isomerism, positional isomerism, functional group isomerism, ring chain isomerism, and tautomerism. Stereoisomerism includes enantiomers, which are non-superimposable mirror images, and diastereomers, which are non-mirror image stereoisomers. Understanding isomerism is critical in fields ranging from drug design to materials science, because isomers can have dramatically different biological activity, boiling points, melting points, and reactivity. Structural or constitutional isomerism occurs when molecules share the same molecular formula but differ in which atoms are bonded to which. There are 3 main subtypes. Chain isomerism arises when the carbon skeleton differs, such as N-butane and isobutane, both C4H10. Positional isomerism occurs when a functional group or substituent occupies a different position on the same carbon skeleton, like 1-propanol versus 2-propanol, both C3H8O. Functional group isomerism is the most dramatic type. Molecules have entirely different functional groups despite identical formulas. For example, C2H6O describes both ethanol, an alcohol, and dimethyl ether, an ether. Ethanol boils at 78 degrees Celsius, while dimethyl ether boils at -24 degrees Celsius, because ethanol can form hydrogen bonds while the ether cannot. Ring chain isomerism involves the same formula arranging as either an open chain or a ring structure, like propene and cyclopropane, both C3H6. Let us examine the classic example of structural isomerism, the 3 compounds with the molecular formula C3H8O. The first is 1-propanol, N-propyl alcohol, with the condensed formula CH3CH2CH2OH. The hydroxyl group is attached to the terminal carbon. The second is 2-propanol, isopropyl alcohol, with the formula CH3CH23. The hydroxyl group is attached to the middle carbon. They are positional isomers with different boiling points. 1-propanol boils at 97 degrees Celsius, while 2-propanol boils at 82 degrees Celsius. The third isomer is methoxyethane, also called ethyl methyl ether, with the formula CH3CH2OCH3. This is a functional group isomer. It is an ether, not an alcohol. It cannot form hydrogen bonds between its own molecules, so its boiling point is only 8 degrees Celsius. These 3 compounds demonstrate how dramatically properties can change based on how the same 3 carbon atoms, 8 hydrogen atoms, and 1 oxygen atom are arranged. Stereoisomerism deals with molecules that have the same structural formula, the same atoms bonded in the same order, but differ in the spatial arrangement of atoms in 3 dimensions. This is a more subtle form of isomerism, but has profound consequences, especially in biological systems. There are 2 major categories of stereoisomers. Enantiomers are pairs of molecules that are non-superimposable mirror images of each other, like left and right hands. A molecule that is not superimposable on its mirror image is called chiral. The most common cause of chirality is a carbon atom bonded to 4 different substituents, called a chiral center or stereocenter. Diastereomers are stereoisomers that are not mirror images, including cis-trans isomers of double bonds and rings. Unlike enantiomers, diastereomers have different physical properties. The key distinction is that enantiomers have identical physical properties in an achiral environment, while diastereomers always differ in physical properties. Chirality derives from the Greek word for hand. A chiral molecule exists as a pair of enantiomers. The 2 enantiomers of a chiral compound rotate plane-polarized light in opposite directions. One is dextrorotatory, rotating light clockwise, labeled with a plus sign, and the other is levorotatory, rotating light counterclockwise, labeled with a minus sign. A 1-to-1 mixture of enantiomers is called a racemic mixture, which shows no net optical rotation. The absolute configuration of enantiomers is assigned using the Kahn-Ingold-Prelog priority rules, designating chiral centers as R from the Latin rectus, meaning right, or S from sinister, meaning left. The classic example of chirality is bromochlorofluoromethane, CH*ClF. This molecule has a single carbon bonded to 4 different atoms: hydrogen, bromine, chlorine, and fluorine. In biological systems, chirality is crucial because enzymes are chiral and typically interact with only one enantiomer of a substrate. Cis-trans isomerism, historically called geometric isomerism, is a type of diastereomerism found in molecules with restricted rotation, typically around double bonds or in ring structures. In alkenes, the pi bond prevents free rotation, locking substituents into fixed positions. When 2 identical substituents are on the same side of the double bond, the isomer is called cis. When they are on opposite sides, it is called trans. A classic example is dichloroethene, C2H2Cl2. The cis isomer has both chlorine atoms on the same side and has a dipole moment, making it polar with a boiling point of 60 degrees Celsius. The trans isomer has chlorines on opposite sides. The dipole moments cancel, making it nonpolar with a lower boiling point of 48 degrees Celsius. For more complex alkenes where cis and trans labels become ambiguous, the E and Z designation from the Kahn-Ingold-Prelog priority rules is used. Cis-trans isomerism also occurs in cyclic compounds, where substituents can be on the same face or opposite faces of the ring. Optical activity is the ability of a chiral substance to rotate the plane of plane-polarized light. This property is measured using an instrument called a polarimeter. A beam of ordinary light passes through a polarizing filter to produce plane-polarized light, which then passes through a sample tube containing the chiral compound. The light then passes through a second polarizer, called the analyzer, which is rotated to find the angle of maximum transmission. The specific rotation, denoted as alpha in square brackets, is a physical constant of a chiral compound, calculated as the observed rotation divided by the product of the concentration and the path length. Enantiomers have equal magnitude but opposite sign of specific rotation. Louis Pasteur first demonstrated this phenomenon in 1848 when he manually separated crystals of tartaric acid into 2 mirror image forms and showed that their solutions rotated light in opposite directions. Quiz question 1. How many structural isomers exist for the molecular formula C4H10? Option A 1, Option B 2, Option C 3, Option D 4. Take a moment to think about your answer. Quiz question 2. Which of the following molecules is chiral? Option A, CH3, CH2, CH3. Option B, CH2 by Cl. Option C, CH bar ClF. Option D, CCl4. Consider which molecule has a carbon with 4 different substituents. Quiz question 3. Which statement about enantiomers is true? Option A, they have different boiling points. Option B, they rotate plane-polarized light in opposite directions. Option C, they are superimposable mirror images. Option D, they always have different melting points. Think about the defining property of enantiomers. Quiz question 4. Cis-trans isomers are classified as what? Option A, structural isomers. Option B, enantiomers. Option C, diastereomers. Option D, tautomers. Remember the isomerism hierarchy we discussed? Quiz question 5. How many stereoisomers are possible for a molecule with 2 chiral centers? Option A, 2. Option B, 4. Option C, 6. Option D, 8. Apply the formula for maximum number of stereoisomers. Problem 1. Classifying isomer type. Classify the relationship between each pair of molecules. Pair A, CH3CH, 2CH2O, H and CH3, CHOH and CH3, CHOH3. Pair B, cis-2-butene and trans-2-butene. Pair C, D-glucose and L-glucose. Pair D, shoot tre si ho have två O and si ho tre och tre. Step 1. Identify the formula of each molecule in pair A. Both are C3H8O alcohols. Step 2. Same formula, same functional group OH, but OH at different carbon positions. These are positional isomers. Step 3. Pair B, both are CH3, CHCs, 3. Same connectivity, 1 cis, 1 trans. These are cis-trans diastereomers. Step 4. Pair C, D-glucose and L-glucose are mirror images, non-superimposable. These are enantiomers. Step 5. Pair D, both C2H6O. 1 alcohol, 1 ether. These are functional group isomers. The classification key. Different connectivity means structural isomer. Same connectivity means stereoisomer. Answer. A is positional isomers. B is cis-trans diastereomers. C is enantiomers. D is functional group isomers. Problem 2. Counting stereoisomers. 2. 3. Dibromobutane has the formula CH3, CH bar, CH birch, 3. How many stereoisomers exist, and how are they related to each other? Step 1. Identify chiral centers. Carbons 2 and 3 each have 4 different groups, H, Br, CH3, and CH bar CH3. Step 2. 2 chiral centers. Maximum is 2 squared equals 4 possible stereoisomers. Step 3. List the 4 possibilities. 2R3R, 2S3S, 2R3S, 2S3R. Step 4. 2R3R and 2S3S are a pair of enantiomers. Step 5. 2R3S and 2S3R are identical because there is an internal mirror plane. This is a meso compound. Answer. 3 stereoisomers total. 1 enantiomer pair and 1 meso compound. Problem 3. R and S configuration. Assign R or S configuration to the chiral center in glyceraldehyde HOCH2CH-CHO. Step 1. The chiral center is the middle carbon, C2. Its substituents are CHO, OH, and CH2OH. Step 2. Assign priorities. O has priority 1 because oxygen has atomic number 8. CHO has priority 2 with C double bonded to O. CH2OH has priority 3 with C single bonded to O. H has priority 4, the lowest. Step 3. Orient the molecule so priority 4, hydrogen, points away from the viewer using a dashed wedge. Step 4. Trace priorities 1 to 2 to 3. Clockwise means R, counterclockwise means S. Step 5. Natural D-glyceraldehyde shows clockwise direction, therefore it has R configuration. Answer. Natural glyceraldehyde has R configuration. Problem 4. Cis-trans identification. Which of the following alkenes can exist as cis-trans isomers? For those that can, identify both isomers. Option A. 1-butene, CH2 double bond CH-CH3. Option B. 2-butene, CH3CH double bond CH-CH3. Option C. 2-methyl-2-butene, CH3, 2C double bond CH-CH3. Step 1. The condition for cis-trans isomerism is that each sp2 carbon of the double bond must have two different substituents. Step 2. Option A, 1-butene. Carbon 1 has H and H, two identical hydrogens. This fails the condition. No cis-trans isomerism. Step 3. Option B, 2-butene. Carbon 2 has H and CH3. Carbon 3 has H and CH3. Both carbons have two different groups. Yes, cis-trans is possible. Step 4. Option C, 2-methyl-2-butene. Carbon 2 has CH3 and CH3, two identical methyl groups. This fails. No cis-trans isomerism. Step 5. Only 2-butene shows cis-trans isomerism. Cis has both CH3 groups on the same side. Trans has CH3 groups on opposite sides. Answer. Only B, 2-butene, shows cis-trans isomerism. Problem 5. Isomer enumeration. Draw and name all structural isomers of C5H12, pentane. Step 1. This is a saturated alkane. Start with the straight chain, CCCC. This is N-pentane. Step 2. Remove one carbon to make a branch. A 4-carbon chain with a CH3 branch on carbon 2. This is isopentane, also called 2-methylbutane. Step 3. Try the methyl branch on carbon 3 of the 4-carbon chain. This gives the same molecule as isopentane due to symmetry. Step 4. Now use a 3-carbon chain with 2 CH3 branches on the central carbon. This is neopentane, also called 2,2-dimethylpropane. Step 5. Total of 3 isomers. Number 1, N-pentane. Number 2, 2-methylbutane or isopentane. Number 3, 2,2-dimethylpropane or neopentane. Answer. 3 isomers. N-pentane, isopentane, and neopentane. Let us consolidate everything we have learned about isomerism. Isomers are molecules with the same molecular formula but different arrangements of atoms. Structural isomers